Welcome to Kenton's videos. Enjoy the video.
You begin by checking the setting. Make sure the function is defined on a neighborhood of the target point and record f at that point. This is your candidate limit. Next, compute basic path limits along x equals x0 and y equals y0 to get quick consistency checks. Once done, test linear paths y equals mx and simple curves like y equals kx2 to look for disagreements. If any path gives a different limit, continuity fails immediately, so test those first and fast. Once path tests are consistent, convert to polar or shifted polar coordinates to capture all approaches uniformly. Set x equals x0 plus r cos theta and y equals y0 plus r sin theta. Then express f, x, y, minus L in terms of r and theta, and check whether it can be bounded by a function of r alone, which goes to 0 as r right arrow 0. If you can find f minus L less or equal to g, r, with g, r, right arrow 0, you prove the limit equals L. Otherwise, refine estimates or search for theta. You finish by verifying that the limit equals f, x0, y0 for every approach. When your r-based estimate forces f minus L right 0 independent of theta, declare continuity at the point. If you encounter a mismatch, produce two explicit paths with distinct limits to demonstrate discontinuity. If neither works, troubleshoot methodically. Recheck algebraic simplification, factor common terms, and try polar or directional substitution again. Errors usually hide in neglected denominators.
Thanks for watching. Consider subscribing if we helped you.